are going to start with the section on radioactivity. Now, at the end of grade 11, we did the chapter, we started with cathode rays. Okay, and radioactivity follows on in that chapter, so it's page 352. Just to recap, because they sort of fit together. When we did cathode rays, we said, what are these cathode rays? Remember, we had to heat up a filament with a high potential difference across it, and it would give off electrons. We said they are fast-moving particles. They have a negative charge, fast-moving electrons. They have momentum. Can you remember the Crookes paddle that could start rolling when the electrons went smashing into them? All right, so they've got momentum. They can be deflected in a magnetic field, and it will be according to the right-hand motor rule with electron current. No? And then it's also deflected in an electric field, and you will find that it is always deflected away from the negative towards the positive, which is an indication that it is a negatively charged particle. All right, so probably then an electron, yeah. I think it will be probably a little bit slower. Okay. The Cathode Ray Oscilloscope, I don't want to say much about it. We had a look at the cathode ray and the deflection between the X and the Y plates. We can use an oscilloscope to measure potential difference of a source. We've done that. Previous period, we've had a look at the photoelectric effect and the quantum theory. I don't want to say much more about that, but these parts all connect up with this next section, and that is radioactivity. Now, when I talk about radioactivity, I think most of you have got a little bit of an idea, oh, it's dangerous, or be careful, or causes cancer. I think there will be various thoughts in your head about it. All right, so what exactly is radioactivity? We say that certain elements, not all of them, certain elements are so-called radioactive. What does this mean? Well, very simply, in the first place, it has an unstable nuclei. The idea of radioactivity is a form of energy that is being given off. If something gives off energy, it tries to go to a lower energy state, which would be more stable than a higher energy state. So it is an unstable nucleus. Just sort of important, radioactivity is a form of energy that comes from the nucleus of an element. All right? So we refer to the nucleus as being unstable. The nucleus gives off energy in the form of something called radiation, and radiation is a collective word. We'll come back to that in a moment. All right. Unstable nuclei can sometimes break down. They literally shoot out a particle. All right. And then it gives off radiation, and it can form a new element. I don't know if you've ever read up about the old alchemists. They tried to change lead into gold. All right, they were never successful. But for example, uranium, which is radioactive, it gives off energy, and it keeps giving off energy or radiation until eventually it ends up as a very stable element, lead. All right. So sometimes, not always, we find that pieces of the nucleus break off, and we will end up with a new element. This change from one element to another is known as radioactive decay. All right, the decay process. A radioactive source, when it's brought near to an electroscope, will charge up an electroscope. The reason for this is when we have radiation and it travels through the air, it knocks off electrons from air particles, and it causes the air to become charged. It ionizes the air. All right. So sometimes we refer to the radiation as ionizing radiation. All right. Ionization implies electrons are knocked off the air particles. What are air particles? Oxygen, carbon dioxide, water vapor, nitrogen in the air. Okay. Now, the radiation that is given off by radioactive isotopes are dangerous. Your body, as you are sitting here, is receiving some radiation. Okay, your body is designed to cope with some radiation. In actual fact, it is some of this radiation that keeps your skin sterile. I don't know if you've ever noticed in the winter if it's very cold, especially if you're in a damp climate, and you keep wearing jerseys, you sometimes get itchy spots on your arms. Don't know if you've ever noticed it. That's fungus growing. Okay? The sunlight, the radiation, keeps your skin sterile. Okay? It kills off bacteria, among other things. So, then you wash off all the dead skins. Okay, people, radiation is dangerous. The first scientists that worked with radiation, I'm referring to Madame Curie, and she and her husband, they all died of leukemia as a direct result of the radiation they received while they were working with it, because they did not realize that it was so dangerous. Okay. We get 3 types of radiation. We talk about alpha radiation or alpha particles. All right, very important, it's a particle. Beta radiation is a beta particle. Okay, so it's literally a particle, like a grain of sand is a particle. The last one, gamma radiation. Where have we done gamma radiation? Yes, it's part of the electromagnetic spectrum. It's a very high frequency wave. Transverse wave travels at 3 times 10 to the power 8 meters per second through a vacuum. All right. So radiation is not a particle. Gamma radiation, people, is an electromagnetic wave. And it obeys all the wave properties, V equals F times lambda. It can be reflected, refracted, diffracted, interfered, etc. Okay. Now, we are going to have a look at these 3 types of radiation and what exactly it entails. Starting off then with alpha particles. The symbol for alpha is the infinity symbol. Okay, it's the Greek letter. Alpha particles. Now, an alpha particle is a little piece that breaks off from the nucleus, and it consists of 2 protons and 2 neutrons. So the mass of that particle would be 4 atomic mass units. All right? Now, 2 protons and 2 neutrons is actually a helium nucleus. So we refer to an alpha particle as being a helium nucleus. It would be a helium nucleus. How many electrons would helium have? 2, without the electrons. All right. So 2 protons, 2 neutrons. Because it's a fairly large particle, it consists of 4 particles in the nucleus. All right? 4 nuclear particles, relatively speaking big. If you think of hydrogen, an atom of hydrogen has 1 proton. A helium nucleus is going to be 4 times bigger because it's got 2 protons and 2 neutrons. So it's a relatively big particle. When it travels through the air, because it's a big particle, it can easily knock off electrons from air particles. So alpha particles cause a very large amount of ionization of the air. One problem with alpha particles, or maybe not a problem, but it cannot really travel very far through the air. It can travel about 1 centimeter. So at this point, if there was alpha radiation in the air, would it affect your body as such radically? No, maybe if you swallowed it or breathed it in. Okay, but it's stopped by a couple of centimeters. So if this was an alpha emitter, would Luan have to worry about it? No, It can only travel about 1 centimeter in air. Because it's a fairly large particle, it's easily stopped. What charge would a helium nucleus have? Rarig. Wil jy vir hulle sê hoekom? Yes, people. A helium nucleus consists of 2 protons. What is the charge on a proton? Positive. And 2 neutrons. What's the charge on a neutron? Nothing. So we have 2 positives and 2 neutrals. What charge do I have? Plus 2. Okay, I have a positive particle. Now, in a magnetic field, if I had electron current, that particle would be deflected according to the right-hand motor rule. Are you with me? Now, I have a positive particle, so it's going to be deflected in the opposite direction. So we can say then, alpha particles will definitely be deflected in a magnetic field, and if you work with the right-hand motor rule for electrons, it's going to go in the opposite direction because electrons are negative. It will go to the opposite side because it's a positive particle. So it's going to be deflected opposite to the direction that a negative particle would be. You can either think of it that way, or you must use the left-hand motor rule to tell you in which direction a positive particle will go. Remember, conventional current goes from positive through the circuit to negative, so it's actually a positive particle that is moving. Do you follow me? Okay. The next property, it will slightly be deflected in an electric field. And it will be deflected away from the positive plate. Now, it will only be deflected slightly in terms of a single electron being deflected. An electron is a very light particle. It will experience more deflection. So a heavy positive particle, it will be deflected, but not radically. Okay, so it's slightly deflected, it's slightly deflected slightly, okay. It's just deflected slightly in an electric field, and the direction would be away from the positive plate. Why? Like charges repel. A helium nucleus has a positive charge. It's going to be repelled from the positive plate towards the negative. Alpha particles can only move a centimeter or so through air, and it's very easily stopped by thin sheets of paper. It cannot penetrate a sheet of paper. All right. So if you are wearing a shirt or even your skin, it can't really penetrate that. It does not have a high penetrating ability because it's a relatively large particle. A smaller particle would have a higher penetrating ability. When alpha decay happens, right, we have over here a uranium nucleus. It's in your books. All right, we have uranium, atomic number 92, and they work with isotope 238. That's the radioactive one. It is going to undergo alpha decay, which means it is going to shoot out a helium nucleus. Okay? Going right back to conservation of energy, can I create or destroy energy? No, so I can't really create or destroy matter either. I can't make it out of nothing. So, at the end of this reaction, if I have thrown away 2 protons and 2 neutrons, what will I be left with? I'll be left with 90 protons. I started out with 92. So it'll break up, I'll have 90 there and I'll have 2 there. What mass number would I have? Yes, minus 4, so I would have 230 over there. Now element number 90 is thorium. Zeg weer? Oh, 234, excuse, right, there. Do you follow me? If I go and add that, I should get that. And if I go and add that, I should get that. I still have what I started out with. All right. Although I no longer have uranium, I now have an element thorium. And because thorium is the first product in the radioactive decay from uranium, I will call thorium a daughter isotope of uranium. Yes. They're both metals. Thorium is also radioactive. It will undergo further alpha decay. It keeps doing this till you end up with lead. Okay. I can't use thorium, for example, in a nuclear reactor. No. Okay. No. No, no, not at all. No. It'll have a different melting and boiling point. It will have slightly different densities, conductivities, etc. Okay, it's a unique element on its own. Well, some elements, for example, those in group 1 have similar properties. Similarly, the lanthanides and the actinides would have specific similar properties. Okay, but thorium is also radioactive, but it is not, except for the fact that it is a daughter isotope, it is not uranium. All right. Okay, that is alpha particles. Very important to remember. A helium nucleus is an alpha particle. Consists of 2 protons and 2 neutrons. It's fairly heavy, so it does not have a very high penetrating ability, and it's very easy to stop it. It can't go through paper. Now, the next one is, oh, yeah, I've got the whole range. Uranium goes to thorium, and then thorium has a daughter isotope, radon, and is it radon? No, it's not radon, it is radium, and then radon, and then polonium, and then lead. And lead is stable. Lead won't break down any further. So the decay of uranium, in a uranium mine, you will very definitely get some lead as a byproduct. And even some of the other elements, although they are very sometimes just not very stable. And there aren't many uses for them, so they won't necessarily try and extract them. Radon, this one, is it A? Yes, radon is a gas. All right. The next form of radioactive emission is the so-called beta particles. Now, a beta particle is a fast-moving electron from the nucleus. Now, remember I said to you just a few moments ago, radiation is energy that comes from the nucleus of an atom. Now, the structure of the atom, we have protons and neutrons in the nucleus, electrons around the nucleus. So where does this electron come from? Now, this electron over here, it comes out of the nucleus. But what happens is a proton breaks up and it forms a neutron and an electron. And it's this electron that is shot out. Okay, that electron is the so-called beta particle. All right? Yes, it stays in the nucleus. All right, now, here I've got an equation. I've got carbon-14. Now, carbon-14 is a beta emitter, which means it's going to shoot out an electron from the nucleus. But now remember, if we go and look at the equation on the left-hand side and on the right-hand side, the stuff that I start out with, I must end up with in total, the basics. So here I have got 6 carbon atoms. Over there, I've got 8 neutrons. That's why the mass number is 14, of which 1 proton is now going to break up, and it's going to form a neutron and an electron. So, my atomic number must increase with 1 because I gain a proton, don't I? Well, I don't gain it, but I get a proton in the nucleus. Because, a neutron, I get a neutron. No, it's the other way around. A neutron breaks up into a neutron breaks up. A neutron breaks up, into a proton and an electron. Sorry. Okay. Yes, it's wrong. The neutron must break up. forming a proton and an electron, which means I will gain a proton. The atomic number will increase with 1. Now? Okay. The atomic number will increase with 1. What's going to happen to the mass number? It's going to stay the same. Why? Yes. So what do we know about the mass of an electron? It is so tiny we ignore the mass of an electron. Now you can go and work it out. It is 1,840th or something of that of a proton. But it is so small it's negligible. We ignore the mass of the electron. So the total mass will remain the same. Alright, so we find over here that the mass number remains 14. Here is the electron that is released from the nucleus. An electron has a charge of -1. So if we go and have a look over here at the overall charges, 6, we end up with 7 there, -1 is 6. Okay, the overall charge. The mass number, because an electron doesn't have a mass, the mass will stay 14. In other words, the number in total of protons and neutrons is still 14, although one neutron has changed into a proton and an electron that has been released. Now, this electron, it's a relatively small or large particle. Small. It's very small. It's so small, it almost has no mass. The mass is so little, we ignore the mass. So, beta radiation can travel much further through air. It can travel many centimeters through air. Because it's a very tiny particle, for two tiny particles to collide, the chances of that is smaller. So, it will cause less ionization. So if I have two unknown sources and I can measure the amount of ionization, if there is more ionization, I could maybe say it's possibly alpha radiation. If there was less ionization, there would possibly be beta radiation. There are other things we look at as well. Okay. It will deflect in a magnetic field and it will deflect in an electric field. Charged particles are deflected by magnetic and electric fields. If we look at the deflection in the electric field, we find that this particle is going to be repelled from the negative pole and it's going to go towards the positive electrode or plate. So, it will be deflected in an electric field away from the negative. In a magnetic field, it's simply going to be deflected according to the right-hand motor rule, because the right-hand motor rule is for electron current. And then we will say, well, the deflection of the electron is at right angles to the direction of movement and the magnetic field. All right. The deflection will be more than that of an alpha particle. Why? Is it heavier or lighter? Lighter. Is it easier to push a heavy object or a light object? Of course, a lighter. So the electron, the beta particle, will be deflected a greater amount than the alpha particle. We can reduce the amount of beta particles by very thin sheets of aluminium, for example, aluminium foil. It will be stopped by approximately 5 millimeter sheets of aluminium or thin lead sheets. Why lead? Lead is very dense. Okay, so the nuclei are closer together in the crystal lattice, so it's harder for something to get through it. That is why they use lead to stop the radiation. All right, it's fairly cheap and it's freely available, etc. Okay, that is beta radiation or beta particles. I'm going to stop with gamma. We've done gamma. Gamma radiation is not a particle. What is gamma radiation? An electromagnetic wave. one having very high frequency, energy is directly proportional to the frequency. Okay? It will cause very little ionization. Why? It's not a particle, so it can't so easily knock off an electron. Okay? It will not be deflected by an electric or magnetic field. Why not? It's not charged, so it can't be deflected. It can travel up to several meters through air because it's not a particle. Okay, it can travel quite far. It will have a very high penetrating ability. We would be able to absorb it using very thick sheets of lead, but it can very easily penetrate paper and aluminium. It will be absorbed, but not perfectly stopped with thick sheets of lead. So if they want to stop gamma radiation, the Large Hadron Collider in Switzerland in Bern, do you know where it's situated? Where? Where? On top of the ground? In a skyscraper? Deep below the ground, built into a chamber, and there will be thick concrete walls and thick layers of lead in the wall to prevent gamma radiation from entering. Okay, very difficult to stop it. Alpha and beta emitters. Certain elements are alpha emitters, certain elements are beta emitters. It just depends. For example, the uranium was an alpha emitter. Carbon-14 is a beta emitter. But whether it's an alpha or a beta emitter, the moment it shoots out a particle, there's a hole in the nucleus. So the protons and neutrons that are left have to rearrange to fill up that hole. The moment they do that, they give off a burst of gamma radiation. All right. So any alpha or beta emitter will give off gamma radiation, and then we find that some other elements, without being alpha or beta emitters, will give off gamma radiation. All right. We will stop.
This lesson is proudly...
Win free airtime with #LearnOn1. Share your comments on the lessons. WhatsApp your feedback, name and town to 081 200 6659. #LearnOn1. Invite learning in.
Right, grade 12s. Last week, well, we started off with radioactivity. I said to you it is energy that comes from the nucleus of an atom, and that we get three types of emissions. They are alpha, beta, and gamma. Why is my... Oh, okay, there we start. Okay. We said then we get alpha, beta, and gamma radiation. All right? Alpha, beta, and gamma is the electromagnetic wave. Then we started and we had a look at alpha radiation, and we said that a helium nucleus is released every time forming a new daughter isotope. All right. And then we said that some of the daughter isotopes are unstable and they form other daughter isotopes. So we get a whole emission spectrum of daughter isotopes. Then we started with the beta particles. Beta emission then is a fast-moving electron that comes from the nucleus. And it is important here, I've got a typing error. It is a neutron that breaks up into a proton and an electron. Okay, and we find then that this electron is the one that is shot out from the nucleus. We said, does it affect the mass of the element? No, but what is going to happen? Because we now get an extra proton, we have a different element, one atomic number up. Okay, so there was the example we used of carbon-14. Carbon-14 is unstable. It emits a beta particle. The way we write a beta particle is like that. Okay, and we end up with an atom of nitrogen. We said that the beta particles, because they are smaller, they can travel further through the air and they have a slightly greater penetrating ability. We also said they are negative particles, so they are deflected in a magnetic and an electric field accordingly. In the magnetic field, according to the right-hand motor rule, and in the electric field, it will be deflected away from the negative plate to the positive one. Then gamma radiation, we had a look at that. We said it's not a particle, but it is very high frequency electromagnetic radiation. Remember, we said that the energy is directly proportional to the frequency. All right. It causes very little ionization because it's not a particle, so it's more difficult for it to knock off an electron from an air particle, and because it is not a charged particle, it won't be deflected in a magnetic or electrical field. You with me? Because it's not a particle and because it travels very fast, remember, any electromagnetic wave travels at 3 × 10⁸ through a vacuum and just slightly slower through air. So it's traveling at a very high speed. It's not a particle, so we say that gamma radiation has a very high penetrating ability. To stop gamma radiation, well, it's almost impossible to stop it, but we absorb it with thick sheets of lead and thick sheets of concrete radiation, blocks of concrete. Then we said all alpha and beta emitters, once they've shot out a particle, the particles that are left in the nucleus, there's like a hole in the nucleus, and they have to sort of reorganize themselves, and when they do that, they also give off gamma radiation. I think that was more or less where we ended up last week. We said then gamma radiation, yeah, okay, that is that. Now, the device we use to check to see if there is radiation. Now, there are different ways of doing it, but the most commonly used device, it's the one that you hear if you watch the movies, they've got a little thing in their hand. It's like a tube-like thing, and they hold it near to the source, and then you hear like, it goes tuck, tuck, okay. That is the device that they use. It is called a Geiger Muller tube or counter, all right? Now, it consists of 2 parts. It consists of this part over here, which is the so-called Geiger-Muller tube, and then it is connected usually onto something that counts the number of radioactive particles that there is in the air. How does it work? In this tube part over here, all right, we find, or we have a wire. And across the wire over here and the tube part, we have a potential difference. All right? So what happens is, on the front of the tube, it's just got a screen, a mica screen, okay? And then we find that when radiation enters this tube, it causes ionization of the air in this tube, all right? And the moment there's an ion, if it's a positive ion, this is positive and that is negative, it is going to jump, all right? And it's going to make a little spark. That would be one count. If it's a negative particle, well, it's going to be repelled from the negative, which is the outer part of the tube, okay? And it's going to go to the center filament wire, and it's going to make a little spark. That's another count. Do you understand? All right, so we say the Geiger-Muller tube, we use it to detect radiation. It can also count the number of pulses in a specific time. An electrical pulse is generated. Why is an electrical pulse generated? Because alpha and beta causes ionization of the air. All right, so we get a charged particle that is going to move either to the positive or to the negative, so it's going to make a spark. Then when ionizing particles enters this mica window, it ionizes the air, and a spark will jump between the wire and the tube. Remember, there's an external potential difference across the casing of the tube and this central wire on the inside of that tube. The pulses, or the sparks, if you want to refer to them as that, are counted by the rate meter. It's usually a digital one, and it gives you a specific reading. Now, if I had a Geiger-Muller counter and I switched it on and I left it lying, standing around here on the table, at the end of the day there will be a couple of counts on it. All right? Because no matter where you are, and I've already said to you, from the sun, radiation from outer space reaches the Earth. A lot of it is reflected back by the ultraviolet rays, all right? But some of it does reach us. Some of the elements in our surroundings depends on what materials we have in the ground, etc., okay, are radioactive, so they give off radiation. A lot of it is absorbed by the Earth if it's buried very deep below the ground, but some of it gets through. We call this just normal background radiation. And your body has been designed to cope with normal background radiation. If I had a cabinet full of radioactive uranium, would the background radiation in this classroom be normal? No. Okay? Then it will be higher than normal, and it could become dangerous. Now, so background radiation, it is always there. It's not exactly the same in one place as in another place. All right? It depends on what is in the environment. Okay, so it varies slightly from place to place. But the variation isn't that much that your body is designed to cope with it. End of the story. There's always some radiation. We call this background radiation. And it differs from place to place. And it can differ. I can stand before break and I can take the background reading over here, and if I come in after break and I take the background reading, it can differ. All right? So it can differ from one measurement to the next. Well, because it varies like this, we can deduce that radiation is random. Okay, so when we measure radiation, we need to take many readings and we need to determine an average. Now, this randomness of radiation is, I sometimes think it's a difficult concept for you to understand. If I have some logs of wood and I store them there in my braai place, Saturday night I want to make a braai, so I take my logs, pack it on the fire. I know from experience I've got lots of meat and toasts and stuff that I have to cook on this fire, so I put on a lot of wood. I get a lot of hot coals to cook with. All right? I can figure out more or less what I'm going to need. I know that when I heat up this wood, it's not all just going to go poof and burn in one shot. It's going to burn through at a fairly steady pace. All right. Now, nuclear radiation. If this tube of Prit was radioactive, it will give off radiation. Depending on what it is, alpha, beta, or gamma, or combination of alpha and gamma, or beta and gamma. All right? I cannot make this thing start giving off radiation, and I cannot make it stop. It simply is radioactive and will give off radiation. That's all I know. I cannot tell you from the one moment to the next how much radiation it's going to give off. Because in the next minute, it maybe gives off nothing, but in the next minute, it gives off 3 or 4 or 5 or 10 counts. It is totally random. Very important. I cannot make it start, and I cannot make it stop. Where with my wood, if it's lying on the stack, it's not burning. If I wanted to give off energy, I light the fire. I cannot make a radioactive source start giving off radiation, and I cannot make it stop. That's very important. It's totally random. It is simply a property of that material to give off radiation. All right. Totally random. You cannot control it. We talk about an indication of the amount of radiation that it gives off. It's difficult to measure it from the 1 second to the next second to the next second because the counts will vary. But what we do find, we can say if I had 1 kilogram of this substance, I can work out how long it is going to take to end up with only having half a kilogram that is active. And then it should take that same amount of time and halve the count once again. So we talk about something called a half-life. So a radioactive substance has got what we call a half-life. And the half-life is the time. It's the time taken for half the nuclei in that sample to undergo radioactive decay. All right. Or emissions. Technically it means, let's say this thing had a half-life of 5 days. Let's say I have 1 kilogram. So if I have, let's put it into grams, 1,000 grams, if the half-life is 5 days, after 5 days, I will have left 500 gram, or nuclei, if I want to put it at that, all right? After another 5 days, I will have 250 grams of nuclei left. You following me? All right? Good question. Does it ever go down to nothing? No. All right? So there is always some left. Even though at a certain point, it is so little that we can ignore it. It becomes negligible. All right? Now, having 1,000 grams of something with a half-life of 5 days is not a problem. The big problem with many of the radioactive isotopes, and I'm talking about uranium-238 specifically, their half-lives are literally thousands of years, sometimes millions of years. In other words, I have my nuclear power reactor, I'm generating electricity. Let's say there is 10 kilograms of fuel in it. So after 20 years, my fuel rods have been spent, but now I've got the radioactive waste. Let's say I've got 10 kilograms of radioactive waste. The half-life of the uranium is 100,000 years, let's just say for argument's sake. So my 10 kilograms, I must now go and store it safely for the next 100,000 years, then I will have 5 kilograms left that is still radioactive. That is the problem with the using of nuclear fuels. Yes, yes, it's not a problem. They've got ways of storing it. They vitrify it. If it's metals, they can dissolve it in glass. All right. Then they store them in lead-lined containers, which are stored in chambers below the ground with thick concrete, lead and concrete-lined walls. But can you go and say with certainty that for the next 100,000 years, there's never, ever, 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 ever maybe going to be an earthquake and flooding?
Or some stupid person who thinks, oh, let's open this and see what's inside.
Okay? You can't safely store something from the one day to the next. With a lot of effort, you can maybe do it for a couple of years. But where do you go with the stuff? And you cannot guarantee that something isn't going to go wrong. So the stuff is stored in geologically stable areas. They try and store it as safely as possible, but the radioactive waste at this point is very, very difficult to store safely. You see, sometimes you have to weigh it up. At this stage, burning of fossil fuels is causing havoc. There's definitely global warming. Go for it. No more cars to drive with. You go back to your donkey cart. Or driving a bicycle. I can see us go to Windhoek for the weekend. Sounds good. Not shopping anymore. Okay. People, back to the half-life. You get the idea what I'm trying to say to you. So they say our half-life is unique for a specific isotope. Some of the isotopes that they use in medicine, I know the one that they use to test the thyroid with, they give you a little bit of radioactive iodine. The half-life is 8 days. So after, if they give you 1 gram or 2 grams of the stuff, after 8 days you've got 1 gram left. After 16 days you've got a half left. Okay, so it's negligible because it's got a short half-life. Some of the elements here on the periodic table, these elements, they have half-lives of split seconds. So technically you can't fill a container with them because you've got that and now you don't have it anymore. Okay, because the half-life is very, very short. It's like a split second. All right, so half-life is unique to specific elements. Some elements have long half-lives while others have short half-lives. That you cannot change on an element. It's an inherent property. All right. One very well-known one is carbon-14 has a half-life of 5,730 years. In other words, if I have a sample of 1 kilogram of carbon-14, after 5,730 years, I will have half a kilogram. All right? And after another 5,730 years, I will have a quarter kilogram, etc. Now, this is what they use when they do carbon dating. They reckon when an organism is alive, we eat, for example, carbohydrates. So we take in sources of carbon. Now, in nature, if we have isotopes of an element, they always occur in a fixed, constant ratio. Now, I don't know what the ratio of carbon-14 to carbon-12 is. It doesn't really matter. But the scientists know that if we have an organism that dies now, the ratio of carbon-12 to carbon-14 is a specific amount. So now this organism is dead. It no longer takes in fresh sources of carbon. So what happens now is the carbon-14 is unstable, so the carbon-14 is undergoing radioactive decay. Do you understand what I'm going for? Okay, so now if they know what the initial ratio is, which they do, And they can go and look at an organism and they test that organism. They take a sample and they see what is the ratio of carbon-12 to carbon-14 in this organism. Oh, goodness me, it's half of what it should be. How old is that organism? 5,730 years. Do you follow me? All right. If it's a quarter of what it should be, then that organism is 10, 11,000 years old. Now, it's not perfectly accurate to within a year. But if we are, or if these people are working over 100,000 years, then 1,000 years this way or that way, it doesn't really matter. All right, do you understand? There are better ways of carbon dating. I'm not going to go into that. You can go and Google it if you like. But I think carbon dating is the most commonly known one. They usually look at carbon dating. Do you understand? And they assume that the ratio has remained as it is. There's no reason why it should change. And then they work from that. Okay. We can draw a graph that can help us plot radioactive decay. So over here we have a graph. And we've got the decay of magnesium-28. They have a Geiger counter. They've got the radioactive magnesium sample. And they go and measure the radiations every 10 hours. And they go and mark after 0 hours, our count was 1. After 21 hours, the count was 0.5. After 42 hours, the count was 0.25. So after, where are we now? 20 hours, the count was 0.5. After 42 hours, 41, 42, the count was 0.25. Do you understand? Yes, yes it does. Yes, you don't have that element anymore. It forms the daughter isotope. At this point, we won't go. It's not so important as to what it goes to. It's just it's undergoing radiation. It's giving off. It's not there anymore. Okay, it's something else. It doesn't disappear. It does become something else. All right. So after 126 hours, that is the amount that we have left. So we can plot a curve. All right? There we go. Now we can use this curve to determine the half-life. We simply go and look. We started off with so much. So at what time, half of that is 0.5. So at what time did we have a half of what we had after 20 hours? You can check it again. 0.5, half of that is 0.25. So it should be at the next 20 hours. Yeah, my line is a little bit not neat. So there. Okay. The half-life of this sample from the graph can be determined as being 20 hours. You follow me? All right. Here's another one. This is the decay curve for iodine 131. So we start off with, they've got it as a percentage, the number of counts. So 100%, half of 100% is going to be 50. So there is 50. What count do we get at 50? Oh, okay, we have got 8. It's not very clear. Okay, 8, 16, 24, 32. So, what is half of 50? Going to be 25. So it's, yes, that's the iodine I've been talking about. All right. The half-life of the iodine is 8 days. All right. Now, I've got a question for you. If we have one atom of carbon-14, one little atom of carbon-14, we know its half-life is 5,730 years. When is that thing going to decay? Is it going to decay in the next second? Maybe tomorrow? After 2,865 years? After 5,730 years? Or after 1,000,000 years? Yes. Why? It's random. We only know that there is a chance of half the number of nuclei undergoing decay. Now we only have one. So the decay time can stretch over twice 5,700 years. Do you understand that? You cannot say for sure. We only know that if you have a sample, that of that sample, half will have undergone decay after a specific period of time. But we don't know if that half immediately decays, if it slowly spread out over the next 5,000 years, or if it waits till the last half an hour of that 5,000 years and it undergoes decay. All right, it is totally random. I can't warm it up to make it go faster. I can't cool it down to make it go slower. Yes. Okay, I'll leave that to you. Uses of radioactive isotopes. Uranium, plutonium are used as a fuel in a nuclear power reactor. People, the radioactive source, when it gives off radiation, it is in the form of heat. And this heat is used to boil water, which becomes steam, which is channeled along a system, drives a turbine, drives a generator. Still go back to the heat, yes? It's just what we use to get the heat. Okay. In medicine, you can drink a solution containing a specific gamma emitter. I think it's barium. And then they talk about a barium meal. Then they can have a look and see what is happening in the different parts of your digestive canal. Okay. You can check your kidneys, because your kidneys must filter the liquid. So you can see how much is being filtered per second, how much is traveling through the system, if there are blockages, etc. We will stop.
Win free airtime with One Africa TV. Share your comments on the channel. SMS your feedback, name and town to 555. One Africa TV. It just gets better.
Demand unique insight and analysis. The Football Review is much more than a highlights show. Bold, provocative editorial that goes beyond conventional reporting, setting the agenda for football discussion. Champions League, Premier League, La Liga, Serie A, Bundesliga, Liga 1, and much more. Want genuine insight with hard-hitting editorial? Need compelling premium football content? The Football Review. Best, bar none.
PEP brings you